Meow, hello everyone, I'm a little cat Meow. Do you know, in the upcoming video, my 4 friends are going to present their analysis of a walking frame. You must watch their analysis. I promise you would like it. See you in the video.
Hello, my name is Sophia Erdina binti Muhammad Sabri, and my metric number is 22002375. A walking frame, also known as the walker, is a mobility aid designed to assist individuals with balance and stability issues while walking. Every year, millions of aged people face a common but potentially dangerous challenge of falls. Shockingly, over a quarter of them experience this hazard at least once annually. The aftermath, serious injuries like fractures and traumatic brain injuries. But the impact isn't just physical. Multiple fall risk factors include lower body weakness, vitamin D deficiency, osteoarthritis, difficulties with walking and balance, and environmental hazards. Walking frames is a solution to mitigate the risk. These devices are more than just aids. They help with improving balance and stability. Why is it crucial? With the high incidence and severe consequences of falls, walking frames become instrumental in reducing risk, ensuring the safety and preserving the independence of elder adults. By applying statics and mechanics of materials, which are two branches of engineering, they are widely used in designing and evaluating the performances of medical devices, which helps in assessment of the strength and durability of the materials.
Hi, I'm Fida Shazan Zunizam, and now we'll move on to the methodology. All 5 of the learning outcomes have been utilized to calculate the estimation of static and material performance of a walking frame. The walking frame's dimension is as shown here. The free body diagrams is also used to determine the force conditions on the structure. The concepts of moment and inertia are also used for further calculations of bending and torsional load of the walker. This allows us to find the relationship between its design attributes and stability and predict the deformation of the walker under different conditions. It lets us assess its performance under regular usage and identify the scenarios that may lead to device failure. Several assumptions are established to simplify this process.
Then let's turn our attention to human force calculation. Imagine a real-life scenario. A patient, due to injury or illness, cannot exert force with one leg. In this case, a walking frame becomes an essential tool for walking. For such patients, when using the walking frame, they rely primarily on their healthy leg and arms to support their body weight. Our task is to calculate the forces exerted by the patient body on the walking frame in this situation and how the walking frame distributes these forces to maintain balance. In this calculation, we use the concept of moment. In a balanced system, the total sum of all moments should equal 0. With this principle, it's easy for us to analyze the interaction between the patient and the walking frame. When the patient is standing on the walking frame, to maintain the balance of the system, the total of all forces and moments must equal 0. By calculating this moment, we can estimate the amount of force exerted by the patient on the walking frame. And finally, we found that the force exerted by one hand on the walking frame under specific conditions is approximately 142 newtons.
I'll explain the equilibrium-based analysis. Due to the symmetrical nature of the walking frame, we only let one side of the walking frame, in this case, side ABKL, being calculated as the magnitude and direction of the forces are the same on both sides. All forces are calculated in such a way that the walker is assumed to be stationary. First, we determine the external forces acting on the walker. The type of support that we use for the structure is a hinge support. We draw the free body diagram of each support on K and L. The support reactions are Kx, Ky, Lx, and Ly. Then, we proceed by operating the equations of static equilibrium to determine force on L. We assume the moment at K is in equilibrium to get the value of components of Lx and Ly. After that, we perform the summation of F in x direction equals 0. We will get Kx equals to 111.57 Newton. We also do the summation of F in y direction, then we will get Ky 228.01 Newton. Next, we want to calculate the internal forces of the walker by isolating each member of the frame and draw a free body diagram showing all external forces and members acting on the member. We assume the behavior of each member, whether it is in tension or compression. We first look at the member of AGK to get the value of Gx and Gy. We perform the sum of the moments of all forces above A to get G. We also do the summation of force in x direction equals to 0 to get the Ax. Use summation of all vertical forces to get Ay. Subsequently, for member of APB, we perform the same methods as previously explained. Perform the equilibrium summation of Fx and Fy, we will get Bx and By. After that, we use the sum of forces in the x direction to get Hx for member of GH and sum of forces in y direction to get Hy. For the last member of BHL, we can conclude the force components at B, H, and L as such. The following static analysis is to determine the moment of inertia. All bars of the walking frame are the same in size and material, so we choose one bar to calculate the area moment of inertia and the polar moment of inertia. Given that the thickness of the wall of the bar is 1.2 mm and the diameter of the bar is 30 mm, we determine the area moment of inertia of this circular section by employing this formula, and we'll get 1.128 times 10 to the power of -8 meters power 4 approximately. Then, to determine polar moment of inertia denoted by G0, we use this formula and get 2.255 times 10 to the power of -8 meters power 4.
Moving forward, we are now focused on the stress and strain analysis. When discussing the use of working frames, safety is undoubtedly a crucial factor. Our primary task when people apply force to the working frame is to ensure it does not disassemble or break. Products that shatter like this are clearly unacceptable. So how can we make the design of the working frame more robust and less prone to failure? This brings us to some important properties of materials. First is ultimate tensile strength. It's the maximum tensile strength that a material can withstand without breaking. But does it mean that if we apply force below this level, the material won't fail? The answer is no. Next, we consider yield strength. It's the maximum stress that a material can take before it starts to deform permanently. If a material is frequently subjected to stress above its yield strength, it risks fatigue failure, well, much like the human body. Lastly, for shear forces, we need to consider shear strength. It's the maximum strength the material can withstand under shear forces. Sometimes the force applied can cause torsion in the handrails of the working frame, leading to rotational deformation. This is another critical factor to consider when selecting materials. Now, our next step is to calculate the maximum load-bearing capacity of the handrails on the working frame under different strength conditions. We have considered two materials, stainless steel and aluminum alloy, and derived relevant data based on their respective moduli. Let's briefly touch on the concepts of stress and strain. Stress is the force applied to a material divided by the area over which it's distributed, and strain is the deformation or displacement it experiences in response to that stress. For stainless steel, the estimated load-bearing capacity under yield strength and ultimate tensile strength is approximately as shown. And next, these are the calculations for the aluminum alloy. So compared to the forces we calculated for the working frame, the load-bearing capacities of this material seem very large. Even we amplify the original force by tenfold. However, where the material itself is not subjected to aging or failure, inadequate welding could potentially lead to structural failure. Plus, here we also need to introduce a key concept, the safety factor. The safety factor is an essential engineering concept used to describe the margin of safety in structures or mechanical components under anticipated loads. The higher the safety factor, the safer the product is in extreme situations. In other words, a design with a high safety factor means that the working frame can remain stable and safe even in very unusual circumstances. So, where our working frame design considers enough strength for daily use, by choosing the right safety factor, we ensure that it provides the necessary safety even under unusual high stress.
Now, we will calculate the deflection of the working frame. This formula here is described as the maximum deflection of a beam subjected to uniformly distributed load on the supported beam. First, we need to calculate the moment of inertia of the beam. We just insert the values of the beam, in this case 0.015 and 0.0012 meters, into the hollow cylindrical moment of inertia formulas. We will get 1.128 with the exponential of -8 meters power of 4. Then, we calculate the Q, 99.4 over the B, 0.08, we get 1242.5 Newton meters. The length is 0.3 meters. We just apply these values with the modulus of elasticity of the materials, then we can get a W max. So, for the maximum deflection of stainless steel, with the modulus of elasticity of 200 gigapascal, we get around 24 micrometers of deflection. For the aluminum alloy, with the modulus of elasticity of 69 gigapascal, we get around 70 micrometers of deflection. So, aluminum alloy has a higher amount of deflection than the stainless steel. Then, we can determine the equivalent mass needed for the beam to experience a 1 mm, 5 mm, and 1 cm of deflection. For the stainless steel, it's 400 kg, 2 metric tons, and 4 metric tons. For the aluminum alloy, it's 145 kg, 730 kg, and then 1,500 metric tons. So, the stainless steel is more resilient to deflection than aluminum alloy.
Hello, I'm Maurice of metric number 2211253. We'll explore how stability and tipping moment affect the stability of a working frame when subjected to external forces. Well, the stability moment denoted as Ms, depending on the frame's weight and the horizontal distance x from the center of gravity to bracket axis. Let's look at two scenarios, a frame with doubled mass and a frame with double weight. Both offer stability moments twice as large as its original design. Then let's move to the influence of gravity center shift. L even low shifts the center of gravity. In this case, from x to 0.5 can halve the stabilizing moment. However, shifts to another direction might increase resistance to external forces, depending on the gravity center and the force location. Now let's discuss the tipping moment mt, which is influenced by the external force and the vertical distance from application point to previous axis. In this case, the height to the base. Again, we consider two cases: a force doubled from F to 2F, and the force applied as doubled height from H to 2H. In both cases, tipping moment doubles, increasing the risk of tipping over. From our previous analysis, we conduct two strategies to maintain stability of the walking frame. One is to increase the stabilizing moment by enlarging the frame space area and weight. Another is to limit the tipping moment by ensuring correct usage and avoid unpredictable external forces. However, in real-world designing, we cannot increase the base area or weight infinitely. Also, we cannot prevent all unwanted forces. Thus, it's important to balance all these factors in an acceptable range to optimize the safety. Previously, we discussed factors of walking frame performance in terms of statics and mechanics of materials. In this part, we will talk about what functioning improvement can be made to improve the experience. For traditional walking frames, users have to regularly lift the frame to walk, requiring a relatively stronger upper limb. Hence, some have modified the sport fit with wheels. Fixed wheels and swivel wheels are utilized in many designs. The former offers a single degree of freedom, while another one provides excellent flexibility. Users can choose either one depending on different usage. Wheel size and weight vary as well. Those with larger diameter and weight provide excellent passability as they lead to a smaller incline angle when overcoming obstacles and a lower pressure to the ground. In that, they are less likely to sink in soft ground. Furthermore, improvements like adjustable designs on handles and legs accommodate different users and provide a more natural posture. Extensions like removable seats or blankets offer a variety of functions to facilitate daily use. Also, some have added handbrakes to ensure the safety. Aside from meeting diverse needs of users, one more challenge is potential failure due to corrosion. I won't explain this in detail as your high school chemical teacher might have explained this thousands of times. Let's go straight to the result. This may damage the protect layer on the surface of the interval. You might think, oh, I just prevented from fluid, shall be okay. Yeah, of course you can. However, there is actually a term called stress corrosion, which can be induced by stress concentration resulting from manufacturing, like in pulper welding. This makes the structure less resistant to corrosion. Thus, effective prevention not only from the view of daily use but for designer are crucial. For most cases, regular cleaning and plating may help with reducing corrosion. For aluminum, the underlying process creates a thicker artificial layer to resist corrosion, and appropriate design and proper welding process can reduce stress concentration, minimizing stress corrosion.
To sum up, we have investigated the walking frame by applying the knowledge of statics and mechanics of materials according to all the 5 course learning outcomes that we have learned throughout the semester. The walking frame is assumed to be stationary for us to perform equilibrium-based analysis. Free body diagrams are drawn to show all the forces acting on the walking frame. Not to mention that we have also identified possible factors and forces which cause failure to a walking frame. Last but not least, further studies have proven the reliability and safety for the walking frames made from AISI 304 stainless steel and 6061 T6 aluminum alloy. These are the references that we have used in calculating our report. That's all from our group. Thank you.